Hi. So last time we introduced the field of fractions. QR for any integral domain R. And further, we proved that if we have some matrix of size n by n with entries in an integral domain R, then the determinant of the matrix is 0 if and only if the columns of A are linearly dependent. Okay, so today we'll more or less finish off our coverage of determinants. And today we're going to focus on actually computing determinants, at least for small matrices. So let's start with some examples. So to remind you, if we have some matrix, then determinant is given by the formula. So it's a sum of all permutations of sign of the permutation times the entries A1 sigma 1 up to A and sigma n. Alright, so let's do some examples. So if A has size, so let's assume that A has size n by n, and do some examples for matrices of small sizes. So first of all, if n equals 1, so it's just a 1 by 1 matrix, so it's just given by some scalar A11 in R, well then S1 is only one permutation on a set with one element, it's just the identity. So the determinant of A is just sine of the identity times A11, and sine of the identity is 1, so it's A11. Next example, if n equals 2, then A is a 2 by 2 matrix. Let's assume it has entries A11, A12, A21, A22. Then there are two permutations on two elements, namely the identity and the permutation tau, which is a transposition taking 1 to 2. So these are the only two permutations on the set with two elements. And now the determinant of A is a sum over these two elements. So it's the sum sine of the identity times A. So here's the formula we're using up here. So it's going to be A1, identity of 1 is 1, times A1, identity of 2, that's 2, plus sine of tau, A1 tau 1, A2 tau 2, should have been A2 2. but tau 1 is 2 and tau 2 is 1. So first of all, sign of the identity is 1. So you have A11, A22. Tau is a transposition, so sign of tau is -1. So negative A1, tau 1 is 2, A2, tau 2 is 1. Okay, so if you have a 2 by 2 matrix, like up above, then to take the determinant, it's just A11, A22, so the entries along the first diagonal minus the entries, the product of the entries on the off diagonal. Okay, so the one other case that's easy is that if we have the identity matrix of size n by n, then we saw last time that the formula for the determinant applied to the identity matrix gives you the determinant of the identity matrix is always 1. Okay. So what about, so now we know the determinant of the identity matrix is 1. We know the determinant of a 1 by 1 or 2 by 2 matrix. So what about for larger matrices? 3 by 3 or larger matrices? Well, then what we have is an inductive formula for the determinant of an n by n matrix in terms of determinants of matrices of size n minus 1 by n minus 1. Okay, so let's start for definition. Let A be an n by n matrix then for each ij, the ij cofactor is the n minus 1 by n minus 1 matrix obtained by eliminating the ith row and the jth column of the matrix. So the ij cofactor, let's call it aij, is defined to be the n minus 1 by n minus 1 matrix obtained from A by deleting the ith row and jth column. So then the theorem is going to tell us that we can compute the determinant of our n by n matrix A in terms of the determinants of the ijth cofactors. So the theorem, which is called the cofactor expansion formula, tells you the following. it says let A be some n by n matrix with R a ring. Then if you fix any I, and the formula will tell us that you can do a cofactor expansion along the ith row. So here's what it tells us. Fix any I, then the determinant of A is given by the formula minus 1 I plus 1 times AI1, the first entry on the ith row. Then we have determinant of the cofactor AI1. And you need to add in minus 1 to the I plus 2. And we look at the second entry on the ith row, AI2, and multiply it by the determinant of the cofactor AI2, and so on, until we get to the last entry on the ith row. So we can do this for any row, and this is the cofactor expansion along the ith row. Okay, let's do some example. So suppose we have the matrix 1, 2, 3, 0, 4, 5, 0, 0, 6. Then we can compute determinants by using, say, the first row. So compute, let's call this A. Let's compute the determinant using cofactor expansion along first row. Well, then we would take first of all the first entry on the first row, and that's 1. So it's going to be so minus 1 to do this formula. Let's set I to be 1. So the first term would be, so if we want to do it along the first row, I is 1, minus 1 to the 2, it's the first entry, that is 1. So it's now take the first entry, A11, that's 1. So it's going to be 1 times determinant of the cofactor A11. That's the submatrix that we would get by eliminating first row, first column, so it's this thing. Okay, so the first entry in the expansion is 1 times determinant 4, 5, 0, 6. Then we need to, so now the next term will be minus 1 to the I plus 2. That's going to be minus 1. And then we're going to need to take the second entry on the first row. That's 2. And then we need to take the matrix that we get by eliminating the second column and the first row. So it's minus determinant 0, 5, 0, 6. Then lastly, we want to take this entry. So 1 minus 1, next is going to be plus 1. Plus determinant plus, sorry, here I put the entry 2. Plus 3 times determinant for the entry, the last entry on, so we should have here the first entry on the row, second entry on the row, third entry on the row. Now the other term we need is a determinant of the cofactor that we get by eliminating the first row and the third column. So that is 0, 4, 0, 0. So that Okay, so let's compute this. So we have 1 times this determinant. So the first determinant of the first matrix is just 4 times 6 minus 0 times 5, so that is 24. Here it's easier because this is 0, this is 0. So the answer we get is 24. Okay. But we could have also done the cofactor expansion along a different row. And here you see it might be convenient to do it along the third row. Because in the third row, all entries are 0 other than the last one. So if we do it along the third row, then we're going to have, okay, so here I would be 3, minus 1 to, the first entry will be minus 1 to the 4, that's 1. So it's going to be positive 0 times something times some determinant some 2 by 2 matrix, but it doesn't matter because it's 0. The second entry is also along the third row 0. So it's going to be minus 0 times something, and then plus 6, in a non-zero term, 6, then we have to eliminate third row, third column, times the determinant of 1, 2, 0, 4. But the determinant of this is 4, so this is 6 times 4 equals 24. Okay, so at least we got the same answer using either the first row or the third row. And you can do cofactor expansions along any row. Okay. Okay, so before we can prove the cofactor expansion, let's recall that we can think of determinant as an alternating multilinear map. So determinant gives an alternating multilinear map. So thinking about determinant as having as input n columns gives us an alternating map from the columns of a matrix to R, where elements of E are thought of as columns. So here E should be R to the n. Thought of as columns. Let me just say a space of columns. And we've already seen that determinant of the columns E1 up to En, that is where EI is the column with 1 in the ith entry, so the standard basis for R to the n, then the determinant of the columns E1 up to En, well, together these give you, these are the columns of the identity matrix. So this is determinant of 1, 0, 1, so just write it like this. And we know the determinant of the identity matrix is 1. So determinant has the property that it's an alternating multilinear map acting on columns of a matrix, with acting on n columns of a matrix, with the property that the determinant of the standard basis E1 up to En, or equivalently determinant of the identity matrix, is 1. Okay, so let's now prove that the determinant is the only alternating multilinear map with this property. So proposition determinant is the unique alternating multilinear map with the property that determinant of the standard basis is 1. So proof. Let F be, so I want to prove that determinant is the only alternating multilinear map which takes E1 up to En to 1. So let F be some other alternating multilinear map with this property. I want to prove that F is a determinant. Okay, so what we want is that if I take any alternating multilinear map, sending E1 up to En to 1, and I want that F is the determinant. Okay, so let's see how F acts on n arbitrary columns. So let A1 up to An be columns in E. Well, then E1 up to En gives us the standard basis for the free module R to the N. So E1 up to En forms a basis for the free module E, and that means that A1 up to An are linear combinations of the standard basis. So let's write each of these columns A1 up to An in terms of the standard basis. So I can write each column as a linear combination of E1 up to En. And let me put the coefficients as Aij. Okay, so if I write it like this, then since the EIs are the standard basis, then this is just this is just a fancy way of saying that the Aij's, as chosen above, are the entries of the matrix with columns A1 up to An. So then, since EI, by definition, 0, 0, 0, 1 in the ith place, what we have is that the matrix with columns A1 up to An this matrix, is a matrix with entries Aij, where the Aij's are the linear combinations such that each column AI is some linear combination of the EIs with coefficients given by the Aij's. Okay, so what we have is that the matrix with these columns is the matrix Aij's, where the Aij's are precisely the coefficients, letting us write each of the columns A in terms of the basis E. Okay, so what do we have? Well, we have this formula here giving us the columns as linear combinations of the basis E1 up to En, which we can simply do because each of the AIs lie in E and lying big E and little e1 up to en is a basis. Therefore, every column is a linear combination of the e1 up to en. And okay, and what do we know? Well, by assumption, F is alternating and multilinear. So then we have the formula for some alternating multilinear map on linear combinations. So use the formula. So let's work out F of A1 up to AN. But now I can use the fact that we have this linear combination, that the AIs are linear combinations of the EIs. So now we use the formula for alternating multilinear maps in terms of, so we use the formula for linear combinations of elements in alternating multilinear maps. So by star, this can be written as, so here we use star, and the formula for linear combinations in alternating multilinear maps to write F A1 up to AN as a linear combination of F on the standard basis. So the formula is sine of sigma, so for each permutation, so it's a sum of each permutation, sine of the permutation, times now I need to have the coefficients, which are the aij's. So it's going to be a sigma 1, 1, a sigma n 1, times f on the standard basis. And by assumption, this equals 1. So then f of a1 up to an is just given by formula sine of each permutation of a sigma 1, a sigma n. But we know that this is just the same as the formula for determinant of the matrix A. Okay, so what this tells us is that determinant is a unique alternating multilinear map which takes the value 1 on the identity matrix. So it's a unique alternating multilinear map acting on n columns, which has determinant of the identity matrix being 1. Okay, so that's actually one useful, you can actually consider this proposition as giving us a way to think about the determinant. It's simply the only alternating multilinear map on columns, which takes acting on n columns, which takes the columns given by the standard basis for the column space r to the n to 1. Okay, so let's do an application of this. So an application of this proposition is that we can use this to prove the cofactor expansion formula. So let's now prove the cofactor expansion theorem. Okay, so here's a theorem I stated before, and I showed you how to use it in one example of a 3x3 matrix. Let's now prove it. So here's the formula we're trying to prove. Okay, so I'm trying to prove that I can find the determinant of a matrix by using cofactors along any fixed row. So proof, okay, let me just get rid of this. Okay, so, well, I know now from the previous proposition that determinant is the only alternating multilinear map acting on columns which takes the value 1 on the standard basis. So let's use the right hand side and let's prove that it's also alternating multilinear and taking the value 1. Then it will necessarily have to be the determinant. So for fixed I, define a map F from E to the N to R, where E is the space of columns. And let's define it by F acting on columns A1 up to AN. So if I take columns A1 up to AN, let me call the associated matrix with these columns A. And let's define a map on these n columns as just defined by the right hand side of the cofactor expansion. Okay, so it suffices now. So if I just define some map by the right hand side of the cofactor expansion, then to prove that this is the determinant, all I need to do is prove that this is alternating multilinear and takes the value 1 on the standard basis. So it suffices to show that the map F is 1 multilinear, 2 alternating, and thirdly, that it takes the standard basis to 1. So this is precisely the content of the previous proposition. Any map with these 3 properties is automatically the determinant, because then F must be the determinant by the previous proposition. Okay, let's do 1. So for 1, it suffices to show that each of the terms in the cofactor expansion is multilinear. So let's just do this term by term, and if we know that each term is multilinear, then the sum of them will have to be multilinear. So it suffices to show. So remember here that the I is fixed. I is just the row that I'm expanding along. So for 1, it suffices to show that for each j between 1 and n, the map Tj from column space from n columns to R, defined by Tj A1 up to AN, and I want Tj to be the jth term on the cofactor expansion, so let's just make this Aij, determinant of Aij. So it suffices to show that this thing here is multilinear, and then the alternating sum that we have previously would also have to be multilinear. Okay, so we need to show that Tj to be multilinear, that's the same as saying it's linear in each column. So it should be linear in each column. Okay. Okay, so look at Tj, and it's defined by the formula Aij. So you would take the ijth entry of your matrix that you get with the columns, and then you want to take that entry Aij and multiply it by the determinant of the ijth cofactor. Okay, so let's prove that this is linear in each column. Okay, so okay, well, let's look at it. It's certainly it is linear in each column. So I and j here are fixed. This is the formula we have. and I want to prove that this map is multilinear. But it's definitely linear in each column, k not equal to j, right? Because if k is not equal to j, then changing the kth column well, it won't change the first entry, because this, if I'm changing a column different to j, it's not going to change this first entry aij, but it will change the determinant, but determinant is multilinear, so it's linear in each column different to j, since aij then doesn't depend on the column. So aij only depends on, well, it's an entry on the jth column, so it only depends on the jth column, which hasn't been changed if I'm changing the kth column. And if I'm changing the kth column, then determinant aij does change, but so the cofactor certainly changes linearly. That's just obvious from a definition. Whereas determinant also is linear in each column because it's a multilinear function. So it's linear in each column different to j because this entry little aij only depends on the jth column. So if k is different to j, it's unaffected. Whereas determinant is multilinear. So basically, because if k is different to j, then it's linear in the kth column because determinant is multilinear. What about the jth column? So so we should also prove it is linear in the column k equals j. So it's also linear in the jth column. So this is because, well, obviously the term. So if I want to take the ijth entry, then taking the ijth entry aij is going to be linear in the jth column. So this is the entry on the ith row in the jth column, aij. Taking this entry is a linear operation. But if I only change the jth column, then aij is unaffected, because aij means 2. Is the submatrix you get by excluding the jth column and the ith row. So aij, this cofactor aij is unchanged if you only change the jth column. So either way, it is linear. So if so it's certainly linear in each. So it's linear in each column different to j, because the determinant is linear. And if when it comes to the column k equals j, then it's linear because the cofactor is unaffected, but the first term aij is certainly linear in the jth column. Okay, so it's linear in the jth column because this entry aij is linear in the jth column, whereas aij is unchanged. Okay, so now we have that each term is multilinear or linear in each column. And hence the sum of them is multilinear. And we've proven 1. Okay. So let's prove that F is alternating. So then it's, well, let me just say this. It's easy to check that that for F to be alternating, it's enough that if we repeat a column, then F equals 0. So actually we've already seen this. So to check something's alternating, it's enough to know that if you repeat a column, then you get the entry 0. Okay, so let's use this. So let's suppose that we repeat some column B in the kth and k plus 1th place. Then we get 0. Okay, let's prove this. But now let's go back to our formula. So if I repeat a column, then we're going to expand along the ith row. Right, so here we've got a formula. And if we expand along the ith row, well, we've got all these cofactors, but each of these cofactors, almost all of them are going to be 0 if we repeat a column. Simply because if you repeat 2 columns in some matrix and take the determinant, then the determinant is 0. Because the columns, if there's a repetition, the columns will be linearly dependent. And we know the determinant of a linearly dependent columns are 0. Okay. So we need to prove that if we repeat 2 columns, then F will be 0, but what we know is that that of so we can take the cofactors, so we have to have this matrix. So let's first form the matrix. Let me just write it like this. The matrix with these columns, B, B, K plus 2, AN. Then let's form the cofactor. But if J is not equal to K or K plus 1, so suppose J is not equal to K or K plus 1, then if I take the cofactor ij obtained by eliminating the ith row and the jth column, then as long as J is not K or K plus 1, then I'll be eliminating some column that's not B, and I'll still have a repetition in the cofactor. So then this equals 0 because because there's still a repeated column in the cofactor. So as long as J is not K or K plus 1, as long as the columns that I exclude in the cofactor are not either of these 2 columns B, then there will be a repeated column still in the cofactor, and then the determinant is 0 because we know that determinant equals 0 if columns are linearly dependent. And if 2 columns are the same, then they're certainly linearly dependent. If columns dependent. Okay, so what we've just proven is that each term in the formula for F is 0 other than the terms where J equals K and J equals K plus 1. So going back here, where was the formula for F? It's here. We know almost all of these entries are 0. Right, almost all of these guys are 0. The only ones which are non-zero are the entries are the kth and k plus 1th entries. So what we have is that F A1 AI minus 1 B AN is minus 1 I plus K let me call B, let me write this as BI. So here, BI means the ith entry in the column B. So let me write the entries of B as B1 up to Bn. Then if I plug this formula in using the fact that if I go back to the formula for F and use the fact that I know now that when I repeat two columns, then the same is going to hold for almost all of the cofactors. There's still going to be a repeated column there. So the only entries left are given by taking I equals K, and then I'm on the kth column. I need to look at the, go to the ith row of the k column, the ith row of the kth column being B, that's the ith entry of B, so that's a BI, and then it needs to be times the determinant of the I kth cofactor of I1, AI minus 1, B, N. And then the only other term that's non-zero is same thing. Now it's going to be the ith row of the k plus 1's column. That's still B, so that's going to be BI times determinant of the same thing, except that I now want to look at the k plus 1th column. So it will be, let's just write it like this. Let's just put this here, make it smaller maybe, like this. Let's try to make this more legible. BI, k plus 1. Okay, that's the formula we have. Okay, but clearly this cofactor that I get by excluding the kth row, or the cofactor that I get by the kth column rather, or the cofactor that I would get by excluding k plus 1's column, since there's a repetition, these two things are the same. And then, well, this is, since these entries are also the same, and these two differ by 1, this is I plus k plus 1, this whole thing is going to be 0. And this proves 2. And lastly, we just have to prove the property 3. So let's do this very quickly. So lastly, if A is 1, 1, 0, 0, and then I do cofactor expansion, along the ith row. Well, for this matrix, as I go along the ith row, I'm looking at entries A, I, J, and this equals 0 unless, so looking at the entries along the ith row, the jth entry along the ith row, Aij is 0 unless j equals I for the identity. So this means that f of the identity expanding along the ith row is minus 1. I plus I, because the only non-zero entry happens for j equals I, I times determinant of the cofactor that you would get by excluding the ith row and the ith column. That's still the identity, but now the identity matrix of size m minus 1 by m minus 1. 1, 1, 0, 0, where this has size 1 less. And of course, I, so the entries along the diagonal of the identity are 1. And minus 1 to the 2i is 1, so that's 1. And that concludes the proof. So F has the properties which uniquely define the determinant, therefore F must be the determinant. And therefore, determinant can be obtained via cofactor expansions along any row. Okay, thanks for listening.